Hi, this is the video presentation for Lesson 2 in Machine Design, and this chapter is Chapter 3, and it's about stress and deformation analysis, which is very important for a machine designer to know, to understand the stresses and the behavior of the materials that they're going to be using for their machinery. Okay, now the sections we're going to cover in this chapter are, first of all, the objectives of this chapter, Section 1. We'll do Section 2. We're talking about philosophies of a safe design. We talk a little bit about the stress element. You talked about that in Advanced Strength Materials, but we're going to talk a little bit about it now. And then the meat of this chapter, we're going to be talking about normal stresses due to direct axial loads that could be tension or compression, and then deformation under those normal stresses due to tension or compression. And then we're also going to talk about shear stresses due to direct shear loads, and we're going to talk about torsional loads, torque, rotational speed, and power just a little bit. It kind of sets up our discussions for later in the course. And then we're going to talk about shear stress due to torsional loads and then also torsional deformation. Again, a lot of this material should be a review for you. The other sections we're going to cover too, I'm not really going to cover these because, these last 4 sections talk about beams and beam bending. And I'm going to hit those a little bit harder when we talk about shafts and shaft design. But in this chapter, in this lesson, we're going to discuss mostly these normal stresses and deformations, shear stresses, and not so much shear deformations, but shear stresses. And then we'll also talk about torsional stresses and torsional deformations as well. Here's our learning objectives. The first one is to recall the philosophies of a safe design. The second one talks about stress and deformation under normal stresses. Those would be your homework problems. And then the third one is perform stress and deformation analysis for shear stresses. Again, deformation on shear is not something we talk about that in depth. It's a little bit more abstract than deformation in terms of axial or tension stresses. And then we're going to do shear stresses due to torsional loads in circular sections. And then we're also going to perform stress and deformation analysis for beams. But again, we're not really going to talk about beams in this lesson because we're going to hit those a lot harder later. And again, a lot of this material is review for you. Finally, we're going to have our terms here. Our terms are going to be ductile materials versus brittle materials, deformation, fatigue, normal stress, that's tensile and compressive, shear stress, which is direct, vertical, and torsional. And we're going to talk about homogeneous, isotropic, modulus of elasticity, the polar moment of inertia, modulus of rigidity, bending stress, neutral axis, and moment of inertia. Okay, so for your very first objective, we need to talk about what our philosophies are of a safe design. In our lesson last week, we talked about what is a ductile material versus what is a brittle material. Okay, so the first philosophy here has to do with ductile materials. And as you recall from our discussion, ductile materials had a lot of deformation in the plastic range, which means that the part stretched quite greatly. There was a lot of strain, if you will. The stress-strain curve kind of straightened. It kind of elongated out. The part stretched a lot, and then finally it failed. That is a ductile material. And we compare that to a brittle material, which really is that's our harder materials. They're a lot harder, they're a lot stronger, and they don't really go through any plastic deformation when subjected to a tensile stress. They just kind of stretch a little bit through the elastic zone, and then once they get into the plastic region, they just break. Okay? So, for a safe design, when we're talking about ductile materials, we want to keep the service stress levels below the yield strength, okay, such that the part will not fail under static load. Now compare that to a brittle material, if you will. The brittle material, we want to keep the service stresses well below the ultimate strength. Okay, so typically when we apply a factor of safety for a ductile material, we'll apply a factor of safety to the yield strength of the material. And then when we're talking about brittle materials, we will apply the factor of safety to the ultimate strength of the brittle material. Now, we know from our discussion last week that even before the part starts to fail, that there is deformations due to the elastic behavior of the steel. That's like in the elastic region of the stress strain curve, where the part begins to stretch under load, but when we release the load, it comes right back. Okay, so we know that the part under normal loading, even if we keep it below the yield strength or the ultimate strength, is going to have some deflections. And then we as designers need to be aware of that fact. And if those deflections are going to be critical to safety and operation, we need to evaluate those in our design as well. Okay, so you definitely got to keep the strengths below where they're going to fail, where the part's going to fail. And then you also need to keep an eye on the deflection as well, because the deflection could hurt you. And then we're going to talk about a new thing called fatigue, and that's the analysis of the response to repeated loading. We're going to talk about that in Chapter 5 a lot, because under fatigue, you can have parts that fail below the yield strength. And then wear. Wear is another thing we need to be aware of. We have to take a look at wear surfaces, especially on gears and bearings. Any parts that contact each other, we need to be aware that the parts will be subject to wear. Okay, so that was the discussion for the first bullet. In your objectives, recall the philosophies of a safe design. Okay, next. For those of you who've had advanced strength of materials, we talked about an infinitesimal stress element. Okay, so stress analysis is where you determine the point within a load-carrying member that is subjected to the highest level of stress. When you're talking about a bar, for instance, that's subject to tensile loading, if you were to look at the entire cross-section of that bar, you're going to have the same load or the same stress across that entire cross-section. But if you recall back from your statics and strength of materials and advanced strength of materials, when you're talking about a beam, for instance, under beam bending, the stresses can be different at different points in the beam. Excuse me. So what I'm saying is that, along the neutral axis, your shear stresses are the greatest, but your bending stresses are zero. And then as you get farther away from the neutral axis, your bending stresses get really high and your shear stresses go to zero. So what there is a different state of stress at different parts within the material. And one thing as a machine designer you have to recognize is that fact, and that you need to be analyzing the material at the point in which the stresses are the greatest. Okay, that's where the stress element comes in. And then we use that to find the principal stresses. And again, we're not going to talk a whole lot about this. This was something that we covered quite a bit in advanced strength of materials, but I need to be aware that the state of stress at any point within your member that's loaded can be different depending on where you're measuring the stress at. I'm going to stop this movie here and then pick it up with number 8 in the next movie. Thank you.